Welcome back to Discovering Geometry with Mrs. Berry. This is lesson 55. We have already calculated surface area for rooms or floors if we were doing wallpaper or carpeting, but we've always worked with rectangles. In this lesson, we will learn about surface areas of many different solid objects, such as prisms, pyramids, and cones. Surface area is the sum of all the areas of all the faces, also called surfaces, of a solid. For prisms and pyramids, the faces include the solid's base and lateral faces. Here we have the base of the pyramid, and then this triangle would be a lateral face. It would also have a lateral face over here, back behind, over on the side behind, and this side over here. So as the base is a five-sided pentagon, then there will be 5 lateral faces of triangle shape. Here for the prism, we have a base down here and a base up here, and then the sides that are also rectangles. That's the rectangular part of the rectangular prism. In a triangular prism, we have a triangle base and a triangle base over here. The lateral sides are then still rectangular. So how do we find the surface area? Imagine you've cut the solid apart. So on this solid over here, this rectangular prism, we were going to cut all the sides. So if it was a box, you want to cut every side of the box apart. Then you're going to label the dimensions, the height, the length, the width. Calculate the area of each face. So each of these faces are the 6 sides of the rectangular prism. And we'll notice that some of them are the exact same as others. This pink one is the same as this pink one. The sides of it that came out over here, we kind of fall to the side, this orange, and then the blue one would also be the same. So if some of the faces are the same, you only need to calculate once. You're going to calculate the area of each of these rectangles, and remember that if it's the same, you can just list it again instead of calculating again. At the end, you want to add the areas of all the faces to get the total surface area. So in this example, we want to find the surface area of this solid. So we're going to imagine cutting it apart so that we have 2 of these rectangles, 2 of these longer rectangles, and 2 of the top and bottom rectangles. This is how I chose to cut it apart. So I have a 15 by 20 inches, and that would be 180 inches squared. I have a 15 by 6, those were the sides, and that comes out to be 90 inches squared. And then I have the front and the back is 6 inches by 12 inches, which is 72 inches squared. Now remember, I have 2 of each of these, so I'm going to add 180 plus 180 plus 90 plus 90 plus 72 plus 72. All of that was inches squared. My total is 684 inches squared. Imagine you have a cylinder. Cut apart the cylinder. What would the lateral face be shaped like? You could think of it as the label of a can. If you take the label off of a can, what is the shape? It would be a rectangle. So let's find the surface area of this cylinder. If I were to draw each piece, I have a top and a bottom base that are going to be circles. They have a radius of 11 centimeters. And then if I peel off that label, or figure out what the lateral face is, it would be 17 centimeters tall. And across would be what? Well, across would be going around the circle. So it's the circumference of the circle. And our circumference is 2 pi r. So 2 r and pi. In this case, it's going to be 22 pi. And we have 2 of these. For our circle, for our top and the bottom. So what is the area of a circle with an 11 centimeter radius? It's pi r squared. So pi times r squared. That would be 121 for 11 squared, and then times pi. And then we have 2 of them. Then we're going to add the 2 top and bottom to the rectangle here. So back to our rectangle, we figured out the circumference, and then we have to multiply. That is really, the circumference is the base of our rectangle. Then we have to multiply by the height of the rectangle. So 22 pi times 17 will give us 374 pi. So now we are adding 2 times 121. That's 242 pi to our 374 pi. And that total is 616 pi. And then we go back and add our units, centimeters squared. I chose to leave it in terms of pi. That's the more accurate answer. As long as it doesn't get too complicated, you can leave it that way. If you prefer a decimal answer, then you could multiply 616 times 3.14. Most of the time, if you're just working on a problem, you would leave it in terms of pi. If you are getting down to if it's a word problem and you're supposed to figure out, how many cans of paint or how many square feet of carpet, then you're going to want to use a decimal and round to however the problem best states. For a pyramid, the surface area is the area of the base plus the areas of the triangular faces. The height of the face of a triangle is called the slant height. It's different than the height of the pyramid. In this picture, we can see the height of the pyramid is right in the middle, but the slant height is going to be the height for this triangular face, the height of the triangle. We use this cursive L for the slant height to differentiate it from H, the height of the pyramid. Now we're going to go through an investigation to find the surface area of a regular pyramid. What is the area of each lateral face? So in this case, we have an octagon base and we have 8 lateral faces. Each face is going to have a height of L, that slant height, and then the base is going to be B, which would be the length of one side of this octagon. So one lateral face is going to be 1/2 base times height, and height here is that L for slant height. What is the total lateral surface area? So total lateral surface area, in this case, we have 8 of these. So 1/2 base times L, and then we would multiply it by 8. 8 times 1/2 is going to be 4BL. But what is the total lateral surface area for any pyramid with a regular and gone base? So in this case, we had an 8-sided base. What if we just have an n-sided base? So that would be 1/2, base times slant height times n, the number of sides of the base, because that is the number of lateral sides that you would have, or the number of triangles. So you could also write it as 1/2 BLN. What is the area of the base of any regular non-n-gon pyramid? So we're asking, in this case, it's the octagon, but what about if there's any regular base? So any regular polygon, what would the area of the base be? Well, this is back a couple lessons ago, how we broke this base into triangles, and then we use this height of this little triangle, which we called A, the apothem, from the side to the center. So that came out to be 1/2 apothem B, the length of the side, times n, the number of sides of that polygon. Now we want to use our expressions from these two steps to write a formula for the surface area of a regular n-gon pyramid in terms of the base length, the slant height, and the apothem. So we just have to add the base times the total, add the base to the total lateral surface area. So we have 1/2 ABN plus 1/2 BLN. And what things are the same that we could combine, make this a little bit easier? They both have a 1/2, they both have the B, and they both have the N, the number of sides. So 1/2 BN, what we have left on this one is the A for the apothem, and on the second one, L for the slant height. Now we're going to write another expression for the surface area of a regular n-gon pyramid in terms of the slant height, apothem, and the perimeter of the base. So what is the perimeter of the base? It's B, however many times there are sides. So B times N. So the perimeter is B times N. We have that right here. To replace that, we would say 1/2 P, the perimeter, times A plus L. So that would be a simplified expression for the surface area of a regular pyramid, N being the number of sides of the base. Here we have a picture. If we were to put all those lateral pieces together, right side up and upside down, we can see that down here at the bottom, we have half of the bases, or half of the perimeter. And then up and down, we have L, the slant height, because that is the height of this triangle. So this is a parallelogram, and the area of the parallelogram would be the base times the height. In this case, the base is half of the perimeter and the perimeter of the base, the big base of the pyramid. And then the height of the parallelogram would be the slant height. So that would also help us in giving the lateral surface area. Now we're going to investigate the surface area of a cone. As the number of faces of a pyramid increases, it begins to look like a cone. So we can think of it as a lateral surface area of many small triangles. We could also think of it as a sector of a circle. So here's the picture of our cone, and here's how we lay out the lateral surface of the cone. And if you see, it's part of a bigger circle. You could also combine it the way that we just did for that pyramid, being half of the bases of the triangle down here and half of them up here. So what is the area of the base? That should be an easy one. The area of the base is a circle, so it's pi r squared. What is the lateral surface area in terms of L and R? What portion is the sector of the circle, and what is the area of the circle? So what is this portion of the bigger circle? When we laid out the lateral part of the cone, we have this part of a bigger circle. Well, what portion is it? So the arc length gives us the part of the circle. So we know that the part of it is 2 pi r. And what is the entire circle? Well, L right here is the r of this big circle. So from there, it would be 2 pi L would be the entire circumference. So again, we're looking at this as a bigger circle. We see that L is our radius, and so 2 pi times the radius, in this case L, would be the entire circumference. And the part that we want to look at is 2 pi r. Where did we get 2 pi r? That would be the circumference of the base. When we unfold the lateral section, the bottom would be the circumference of the base. So this is the portion of the sector that we're working with. And we can see that we can reduce this fraction by a factor of 2 pi, and we would be left with just r over L. And what is the area of the sector? Well, if it was an entire circle, it would be pi r squared, and our r, or our radius of this big circle, would be L. So it would be it would be pi r squared and r is actually L in this case, L squared. And then the portion that we want would be the fraction r over L. Now we can reduce this because we have an L squared in the numerator, but we have an L in the denominator. So we can say that it is r pi L. We would probably rephrase that as pi RL. The commutative property of multiplication allows us to move or rearrange those as much as we want. So here in step 1, we have the area of the base. In step 2, we got the area of the lateral face. So what is the formula for the surface area of a cone? We have pi r squared plus pi RL. If you want to combine it or make it a little simpler, you could write pi and r. Both of them share a pi and an r. This part then has an r left. This one shares a pi and an r and has an L left. Now in the picture, here is just like the pyramid one. If we were to put the little tiny slivers of triangles together, we would have that it's pretty much almost a rectangle with a height of L and a base of pi r, because it's half of the 2 pi r. And so then that surface area, or this area from the lateral face of the cone is a rectangle that is pi r times L, which is exactly what we figured out as we looked at it as a sector of a circle. Our last example wants us to find the surface area of this given cone. So again, we just found that the surface area of a cone was pi r squared, the area of the base, plus pi r L, the area of the lateral face. In this case, our r is going to be 6 since the diameter is 12. So pi times 6 squared plus pi times 6, and then our slant height will be 10. When you're looking at a picture, make sure that you're taking the slant height, which is the one up here, and not the height of the cone. So this is our slant height, this would be our height. (36 pi) plus 6 times 10, which is 60 pi, is going to be 96 pi. And then we need to look at our units. This was in centimeters, so it would be centimeters squared.